Hello, welcome to today's designTimber webinar. My name's Matt Milton. I'm Editorial and Publications Manager here at Timber Development UK. In a minute, we'll be hearing all about Haileybury SciTech, an award-winning science and technology project in Hertfordshire. But just before that, I'm going to introduce Timber Development UK and tell you a bit about us. We were formed in 2021 from the merger of the TTF and Trada, which makes us the largest, most comprehensive supply chain body in the UK. We span everyone who works with wood. If you work with wood, you belong with us. You can see our three missions here: to connect the supply chain, to lead best practice, and to accelerate a low carbon future. And we achieve these goals via a number of outputs, such as our upcoming UK Timber Design Conference, which is our annual flagship conference for everyone who designs with timber. It's coming up on the 3rd of July in London, so do get your tickets. You can get them from the Timber Development UK website. We also have a number of other outputs. Here you can see a section of some of them. Designing Timber is one of our two magazines. We have Designing Timber and its sister publication, Supplying Timber. All members receive print copies of that, and it covers case studies of inspiring timber buildings, all the latest in timber news, a lot of CPD, a lot of very useful information and timber understanding. Next to it, you can see one of the many other resources in our knowledge library. That is a fairly recent publication about addressing risks of moisture in timber construction, but we have a very comprehensive knowledge library, absolutely packed with a host of other resources like that one. You can also see another example from our knowledge library. There's one of our timber knowledge sheets, particular ones on using SIPs, but we cover anything and everything to do with timber design, construction, supply, sustainability. You will find it in our knowledge library. So do go and check that out. And next to it, you can see one of our case studies, Cotto House. We had a webinar on that particular project recently, and you can catch up with that if you missed it on our YouTube channel. But there's all sorts of case studies on every typology that you can imagine, and you're free to browse them on our website. We do offer an awful lot of free resources, but we would encourage you to join us because members get access to a lot of exclusive member-only content. You also get substantial discounts on things like the UK Timber Design Conference and a host of other membership perks, such as being able to use our Find Your Timber Partner facility, which operates a little like a shop window for your business. So if you're a designer, a supplier, an engineer, an architect, you can really benefit from TD UK membership. I'm now going to hand over to Chris from Hopkins Architects, the first of our three speakers today. Please do make use of the Q&A function. You can find that at the bottom of the screen. And do ask any and all questions that you might have over the course of the webinar, and there'll be a little bit of time at the end to answer them. So over to Chris.
Thank you. We'll share my screen. Yes, sorry for those expecting Mike Taylor for a start. I got a sort of panicked email on end of Friday saying that he had to attend another talk. So you have me, unfortunately. He has put the presentation together, so I am just winging it slightly. But yeah, he's gone through it on Monday, so hopefully all is good. Hopefully you can see this. So it's just a slide for Hopkins. Just shows a sort of vast array of experience and various projects over numerous sectors, and it kind of you know, over the last 40 years, over 40 years. And I think it shows a kind of honest expression of materials and context and engagement with the historic heritage. And as it's a timber development talk, we've just shown a few examples here where we have used timber in the past, particularly internally. And you'll see some of the details here will relate quite directly to Haileybury as well. So Haileybury School, this is the campus basically. We can see the main quad in the middle. We've got the sites at the bottom there. Now, I didn't actually go to Haileybury School, but I did go to school quite close by and did sneak into their football pitches every now and then. So I've got a vivid memory of kicking the ball over the fence from about 3 yards out and probably hitting our site from here to here. So that was quite a while ago now. So yeah, as you can see, the site is to the south. We've got the design technology block. You've got Baker science block, biology, and maths. So, history of Haileybury. It was designed in 1806 by William Wilkins as part of the East India Company and the East India College. It was opened in 1809. Big, strong quad in the middle. It was closed in 1858 and reopened as a public school. So it basically became Haileybury School in 1862. So lots of history. It's also got Humphrey Repton landscape design. So this is also a view from Thomas Medland. I think this might be in the Royal Academy as well shown. So that's just a view from the lake over here back towards the main quad by Wilkins. So it's a running theme really. The quads at Haileybury, you can see a few examples here. You got the main one, and then got the memorial quad behind that, and further up you got the Bartle Frere Edmonton, and then this is looking at the heritage. So you can see there's numerous Grade 2 listed buildings. Now our site is down here, which is close to the entrance of Haileybury School. You've got Hailey Lane, College Road, and then you've got the Baker building, which we're calling, which is also the science block, which is shown as moderate significance. Now this is this was built in 1932, so it has curtilage listing. So that was built pre-July 1948. So basically, it's got the same sort of impact as, or same restraints as the rest of the listed buildings in the area. So we go forward. So they've got a few examples of buildings on site, quite grand, mainly brick, sort of well proportioned, good rhythms to the facades, and that was kind of the context and the inspiration that we drew on. So you got lots of William Wilkins again, and Arthur Blomfield, and Herbert Baker, who will come to that, but he did this building here, which is basically the one backing onto the site, and the one we connected to, which we'll see in a second. So this is coming down from the main quad. We've got sort of language of red brick, so strong red brick throughout, all the way to the entrance. So then existing buildings on the site. So this was as existing. So you got the biology here, which was kind of single story, not in great shape. Asbestos was found throughout. It was noted as detracting from the historic setting by the conservation area. We've got maths here, which didn't actually touch in the end, but we have created a better link to it. We've got design technology, the existing design technology building here. Not massively exciting from the facade, but quite an interesting roofscape, and actually it's a building that was working quite well. And then, as I say, we've got Baker here. So this is looking from College Lane to the quite grand entrance, which again is this image here. So you can see on plan, we've got the entrance here at the minute. Well, previously it was just a corridor, and you got your physics and chemistry labs within. So to the rear, it's a slight level change, very much inward facing, no access to this side at all. It's all kind of coming through here, coming through the main entrance, and actually most students were coming through this sort of side entrance anyway. So DT building existing, again, not like great shape at the time. A few porter cabins which stored quite a lot of excess materials and other bits and pieces that they needed. But actually internally, it was a space that was working for the school. And you can see all the machinery there. And that's it, the other side. So the brief. So essentially, we're taking the four aspects of science, technology, engineering, maths. They wanted to bring them together and create a culture of interdisciplinary learning. So very much collaborative approach. This is a diagram which basically shows what they had existing, what we needed to reprovide. So this is basically what's in biology. If you haven't guessed already, we demolished biology, and this was what we needed to reprovide. And then the sort of solid line are the additional sort of new areas that they wanted to include, including Stanex, which is a sort of pioneering study of genetics, looking at the genetics of fruit flies, essentially, to find cures for cancer and diabetes, potentially. So this was a brief follow. So I'll come on to it in a second, but there was a master plan, and this was the client brief. So the new SciTech building is to be designed and configured with the underlying master plan vision in mind, creating a central courtyard, knowledge exchange garden area between the existing science building and technology building. So again, that's as it was. And this, so as I said, there was a previous master plan. This was it's taken from quite a small document, so it's a bit fuzzy. But essentially, they were looking at a two-phase development, where phase one, they would keep DT, demolish biology, and it's a new building for biology. And then phase two would be essentially demolishing DT and reproviding what they'd lost and anything extra needed in the brief. So in the meantime, there was also this consented scheme back in 2017 for an extension to the DT block, which essentially brought a new line of classrooms to the south and west, and extended it slightly to the east as well. So this model was just lying around in the DT workshop. I think kind of yeah, Mike had a few ideas, and got out his crayons and essentially came up with this concept sketch. So sort of working similar to that, to the image before, but retaining DT, which I think was the main the big move of the project, I think, in terms of sustainability, and I think is kind of won the competition, really. So essentially, we could keep DT. The students could continue working in that space throughout the project, so there wasn't as much disruption. And then we've got, it says physics here, but actually it was ended up with biology and computation labs on this wing here, which kind of extended from the wing of Baker. Got research building here, it's 2 stories. And then that is all connected with a sort of internal cloister. And we've broken through from College Lane through the main Baker building and out the back. So now, so the whole thing was connected, and then got a sort of better connection to maths as well, which remains. So essentially from that concept sketch, it was looked at in a bit more detail, and you can see here again, we've got the 3-story teaching block. So we managed to, with the floor to floors, fit in 3 stories of teaching in to the south, which related to the 2 stories in Baker. We've got the research building to the north, and we've kind of cut off the nose, as it were, of DT, and linked it all together with the cloister. And we've got the link through, got the steps and straight through. So again, ground floor kind of shows the same thing. First floor, that just shows that, you know, we're blank here. We've managed to fit in an extra story. And then going up again, a bit more labs and prep rooms, shared offices. And that is the roof plan. So details and materials wise, again, we were looking predominantly red brick in relation to the context. We've got the stone banding, again, everything's kind of relating back to the original Baker building. And we've got the hit and miss brickwork, which gave a bit more interest to the facade, and actually was used for ventilation of the MVHR units, which I'm sure Patrick will come on to later. And again, the conservation officer also insisted on the roof being turn-coated steel, the standing seam, again, to relate to Baker. We've got the roof lights and louvers, the ventilation, passive ventilation at the top. Carry on. So that's it in its context. So you can see, again, the conservation officer was very adamant that these should all align through exactly with Baker. I won't go into too much detail there. That's the north elevation showing the research block, maintaining DT behind, and the sort of cloister link, single story cloister to Baker. And that's it in relation to Wilkins Quad. And there it is in just after being finished. So yeah, the landscape needed a bit of time to bed in, but you can kind of see how we've created the quad and the courtyard in the middle, how it all relates to Baker. You've got the red bricks relating to all the context here, and very much echoing the sort of quads, courtyards elsewhere on the campus. So that was just a section again. 3D view at ground floor, again showing most of what I had explained before. That this room in particular worked quite well in the end, although we didn't know it was quite an awkward shape, but actually it's one of the favourite spaces in the final building, I think. Just so you've got a view all the way through. You can stand one side and you can see it straight through to Hailey Fields to the east. So where was the timber? We hadn't got to any timber yet. So seeing this is a timber development talk, this is actually an integral visual. I'm sure Matt will have some more on this. But essentially we've got full CLT structure, glulam beams, to the cloister, and yeah, all connected back to the original DT. And I'll probably let Matt go into a bit more detail on that. And then internally, we basically had a fly through that I think I had open on my desktop for a year and a half, just constantly. Just any detail was there, we could just refer to it, and we got some nice nice views from it. So you got your timber acoustic panels linking back to Baker, which is now behind us. Got DT opposite. Yeah, that's the link. I think we slightly underestimated the size of that lintel, but yeah, that kind of gives you an idea anyway. And again, across the courtyard, looking over to research. So internally this is sort of ground floor, well, ground and first floor of the teaching block. Very much wanted to expose as much of the CLT as possible. Obviously, there are points where you can't do that for acoustic reasons or fire, but we're keen to try and keep as much of it exposed where we could. And then you've got the acoustic rafts. And then on the top floor, you'll see in some of the photos, I think the other guys have got it in their presentation, but the timber here did actually get value engineered out, but that was the idea. It was all supposed to be the timber, and then you've got the roof lights, which also had the dampers in the side for natural ventilation. And that's some finished images. Which are, yeah, hopefully they're pretty close to the visuals, really. A few external shots, and I'll just flick through. But yeah, there is a fly through. I showed the guys earlier before the call. That is really good on the Haileybury website. It was a bit jumpy, so I won't show it necessarily. But yeah, if you've got time, go to their website, have a look. So yeah, this was the team. So we've got Matt from Integral Engineering and got Patrick from Atelier 10. So I will pass on to you, Matt. That's okay.
Yes, thank you very much. So I will find the share button, make sure I'm doing the right thing. It is that one. Hopefully that has, it's like the right thing has popped up. Yes, so my name's Matthew Blaza. I'm an associate here, Integral Engineering Design. I've got the obligatory little read as well. Yeah, so Integral are civil and structural engineers. We're based in Bath and London. We have like very much have a strong focus on education projects, on culture projects, and on heritage projects. So it's a kind of really good fit for us. And also we love to design in timber where possible, which, so I promised I'd be quick. Let's get on to Haileybury itself. Always nice to share what it looks like in construction, doesn't it? This is it as it's being constructed. As Chris mentioned, there was a master plan at Haileybury, which was part of the brief that they've got an ambition to get to net zero carbon, but beyond just getting there, they also want the important thing for them was actually the educational side of it. So putting it on show so the students can actually see the sustainability and kind of understand what a sustainable building is. And as a structural engineer, when we talk about sustainability, really we're talking about embodied carbon. So I need to make the embodied carbon, the amount of energy that goes into making that building as small as possible, making Patrick's job later, where he's trying to balance up and generate energy and all that kind of all that amazing stuff they do on that side a lot better. So yeah, a nice small number to start off with means he's not got to work quite so hard, but he's done a great job on that, which he'll talk about later. But what are the targets? iStructy and Letty have slightly different targets. I guess the iStructy are pushing us to give as much headroom for all the other disciplines, but they're very similar numbers, and they're both very difficult numbers to hit on new build construction. Yeah, which we'll get into. So very early stages in Reba 2, what we actually did was we went through and did a scheme design for a mass timber, a full concrete frame and a steel frame and precast planks. And then all this data was presented to the client, and you can see that there's definitely a lower carbon option. This is higher, obviously, than the number you saw on the previous page, but there is a lower carbon option going for mass timber, so you're kind of saving quite a bit. It wasn't just sustainability we were selling this on. We also gave a load of metrics about kind of buildability, about costs, about quality, and giving the client all of that information early on meant that they actually bought into what we were doing. So the VE was mentioned by Chris, but we didn't get to the point where we VE'd out the most sustainable thing, the timber frame. So yeah, the effort early on to kind of get them to buy in was quite an important part of how we delivered this project. So let's actually talk about kind of the engineering of the building. Effectively, there's three bits of this structurally for the new works. So the first one I'm going to talk about is the teaching block. So as Chris mentioned, this is the one that we squeezed 3 stories into the neighbouring 2 stories of the Baker building. And it's kind of this very simple frame where you've got external load-bearing walls. You've got CLT panels spanning between. This one's actually founded on piles, which doesn't really help our embodied carbon, but it's all to do with the fact that we've got clay here, got a lot of clay. It was clay that was going to swell up because there were some dead trees that we had to remove, got replaced. So it's very much within the influence zone of that, which didn't really help our numbers. We got here about 8 meter spans going here. So we've got 300 thick CLT floor panels, which isn't potentially not the most sustainable or the least material option. But one of the things it did give us, it gave us the slimmest build-up, which was really helped in terms of fitting in the extra story. And it also meant that because it was a serviceability governed design, then we were limiting deflection, we were limiting vibration, was the thing that actually sized those elements. We got some extra, it helped when we were looking at acoustics, and it helped when we were looking at charring of these as well. I won't go too much into fire design because it's a very specialized thing, and you could probably spend a whole hour talking about it for each different project. But the way that this building was set up, you've almost had like 3 separate buildings that were side by side with these lovely kind of exposed stairs. And got the timber treads exposed with then stone on the top, which would be a nice way to do it. But each of your compartments is very small, so auto extinction was a lot easier to prove on this kind of project than it would be if it was a kind of big compartments. Then we get to the roof. So on the roof, the pictures of these are set by the neighbouring Baker building. So they're not the most efficient, but they then tie in nicely and kind of all the heritage. From that, any structural engineers out there will tell you that that's not the most efficient place to put those tie bars. But so we positioned them there for 2 reasons. One because the central portion of this actually has a corridor down the sides, so that meant that they weren't passing through there, giving kind of a slightly ugly detail as something passes through a partition wall. And the other one was a bit more kind of practical in that moves it to the point where if you've got any high-spirited students, they're not going to be jumping up there and hanging off this bar. They probably could still get to there when they're standing on the benches or whatever, but I don't think that's the kind of students they have at Haileybury. And then at the peak there, it was a kind of an ideal place to put in roof lights, and you can see the vented panels up there as well, which is then getting into everything that Patrick is talking about. So I won't talk too much on that one. So what are the numbers coming out this one? This one, we were almost, as I mentioned earlier about the foundations, actually, I think we're exactly 50% of the embodied carbon the structure was in getting you up to ground level, and then 50% for the superstructure. So the things we could potentially have saved on is that thickness of the floor, but there were reasons why we went that. So whether we would have ended up with a lower carbon for the entire building if we went for a different option is debatable. So next block structurally was the research block, where we've got this 15 meter by 15 meter on plan building. It was the one that was kind of had the loosest brief. So Chris and his team were playing around with it, or we were all playing around with it a little bit more, looking at different kind of options and sizes and massings on plan. And actually, was this the final design of that in terms of the size was actually driven by where we were partially demolishing the biology building, the one that was detracting from the site. And we've created this building that's kind of is split into two. There's a front half that's very open with this lovely staircase. You've got the wall of that stair is supporting the timber flights, and then the top bit, it kind of actually spans as well, so like kind of sculptural element. And then we've got this butterfly roof light in the middle, which is engineering wise, is kind of like, it's the most interesting thing. This is just the model with everything stripped out. So you can see we've got this ring of glulam beams at the top that come down to a ring of glulam beams at the eaves level, and then hip members expand between them. So a little force diagram. So actually that top ring is acting like a propped cantilever. So the members come out, they're then propped by the hip members. So they're acting in compression and they're trying to spread out. And then the ring at the bottom is stopping all of that from spreading out. So it's actually quite an efficient overall structural form, but did require a little bit of coordination. So with the sizes of those, the underside then of the ring beam at the bottom there, use my cursor, is the head of the windows. So that was setting the depth of those members. And then we were getting the hip members then needed to come down. So the underside of the hip member noded out with the underside of that member, but then came up to the top, and it all kind of fitted together. So there was going round and round in circles of looking at the worst case bit and then making sure that that works in terms of geometry going round. And then we've got this steel node that at the top is all expressed. That again, we spent quite a bit of time modeling that in 3D, looking at how that would work visually, but also how it could transfer the forces over. So we kind of produced some kind of fairly detailed early designs on that, which the project was delivered by BK Structures, and Ingenuity did the kind of the final design for them. And this is what they came up with. But the only difference between this and our stage 3 design is they switched bolts out for driven studs going through. So there was a lot of effort went into that, and we've got this little detail where, thinking about the buildability, this is almost it's a kind of a shelf where the steel, the timber can come and sit on the steel. So thinking about how that gets put up was kind of an important part of how we delivered this. So body carbon, this one is a little bit higher in terms of per meter squared number. So 258, the other one was 25. I can't remember now. I probably should have had it in my head. This one actually was 60% in the ground. And so again, we had, this was strip footings, but we really pushed down the grade of the concrete to minimize how much was in that. But it's almost that the building above maybe wasn't right sized, and we could have gone, if we'd gone more, it probably would have offset the amount of concrete we need to put in the ground. But again, it was driven by the ground conditions, and your ground conditions are your ground conditions, so it's a huge amount. Final bit, cloister, which is, as Chris mentioned, is a kind of the key part of the entire design. And the cloister includes then the links to the two buildings on either side, the existing buildings, and how we then refurbished the areas of those. But so one of the things we did on this project, and that we always push to do on our timber frame projects, and we made sure it did actually happen on this one, is we tendered the timber frame early. So we tendered that at the end of stage 3. We got them in during the stage 4 design. So they were appointed and working away, designing, getting space in factory, etc. Before we then appointed the main contractor, which then made sure that we were going through and checking all those little things that we've coordinated in terms of depths, making sure that connections are hidden, etc. They were then working through and making sure they were actually deliverable, which luckily we had spent the time, which meant they were. And the only real change that they made was a kind of a buildability issue, and that was on this central cloister. They changed it to allow so the two main buildings went up, the timber frame went up with those. Then these big long brackets stick out and pick up the cloister timber later on. But the brickwork was then built past, which helped Chris with his detailing in terms of waterproofing and lots of the kind of like sequencing works And then they came back with a later site visit to install that. So that thinking about how it's actually going to get put together, the final kind of panelization and whatnot, all then came earlier on so that we could deliver it smoothly on site and make sure it was open in time for the terms. So I think what Chris mentioned at the start, the obviously adopting a timber frame is the way to reduce the embodied carbon as much as possible for the new structure. But the thing that actually really helped us, we were really close to being an A, 154. So it was if we got to 150, we would have been an A. And so we were under the LETI target, not quite at the iStruct target. But the biggest thing that we did was keeping the two buildings, or definitely keeping the DT and kind of linking in with the other buildings. So there's effectively you're creating a larger building with a lot less energy because you're making use of what's there more. And it's so then I've put down there the biogenic carbon, so that's how much carbon is locked into that timber frame. Again, that's another kind of hot potato about whether you should be using that or not. But I think that getting the embodied carbon, the actual structure, the top number as low as possible makes Patrick's job to then get to net zero a lot easier, at which point I will seamlessly hand over. Hopefully hit the right button.
Thanks, Matthew.
Not entirely seamlessly, because I'm just going to jump in and remind everybody about the Q&A box. So do ask questions, and I'm sure you must have some. So yeah, enough from me. Back to Patrick.
Thank you. Just sharing my screen, anything coming up? There we go. Well, good morning or good afternoon, everybody. I'm Patrick Bellew. I am an environmental engineer, and I was the founder of Atelier 10 way back in the dark depths of history. In fact, we set the business up in 1990, and I'm wondering why my slides are not going on. Okay, so founded in 1990. I'm going to zoom through this first bit then. We're building services engineers. We were also the environmental engineers and lighting designers on the project. Our world has always been around high performance building design across many sectors, and we have been working for 35 years really on trying to design more environmental buildings that do more with less, which I think is something that's I guess is a familiar mantra, and Matthew and Chris already addressed. I worked with Hopkins personally for more than 40 years. I've worked on an infant school, I think back in about 1980 something, in Fleet in Hampshire. But more recently, we did this lovely building at Croon Hall in the Yale School of Forestry, which was heavily emphasizing timber and heavily emphasizing particularly different ways of distributing services in buildings that are relevant to this project. And then more recently, the multi-award-winning WWF headquarters building in Woking, which also makes extensive use of timber and timber construction in its various guises. So we have a very close working relationship with Hopkins, and that sort of confidence in one another was very helpful in the project. So what we were doing with the project as a whole, as a brief, was to try and minimize carbon dioxide. In terms of the statutory requirements, the East Herts planning policies sort of an energy hierarchy, which is fairly consistent with most others, around reducing demand through passive measures, efficient services, and then looking at zero carbon technologies, and then finally offsetting. But there was no specific requirement for us to benchmark or to submit energy figures beyond the building regulations. So as it turns out, we did a lot of the work in the background, but we didn't actually produce a BREEAM rating or for the building, which is just the client didn't feel they needed to do it because it wasn't part of the planning. So the low carbon roadmap that we're all kind of familiar with on buildings, which is, how do you use passive design around the way that the building is organized, daylighting, good ventilation, mixed mode ventilation, those sorts of things, high quality building materials, active systems, which, to do with the ventilation and the types of heating, potentially with efficient plant, in this case using ground source heat pumps, and looking at PV on roofs. So all of those in the course of project decisions get the carbon emissions lower and lower. But I think it's interesting to reflect that in where we are now, really, since, in the way that things are thought about, and as Matthew has alluded to, this sort of pathway to net zero intertwines embodied carbon and operational carbon in a big way, because you have to now be much more cognizant of the embodied carbon, because in reality, when you have heat pumps for conditioning and you have potentially plenty of renewable energy in our power supplies, the embodied carbon is a much bigger part of the impact on a 2030 building, or a building today, or looking forward to 2030. And some of the decisions that we make, if you put things, a lot of, for example, aluminium shading on the outside of the building, do a tiny amount of reduction in heat gain, you don't necessarily ever get that carbon back. So a lot more of the work we're doing, and we did on this project, was around how do you balance the embodied and the operational carbon, which is a big question these days. And so what that comes down to is very much about agreeing the brief early on, because the big question was, do these labs and teaching rooms, how much of them would need to be mechanically ventilated and conditioned? How much of them could rely on natural ventilation? Because the building mimics or apes the forms of older buildings that predate mechanical systems, the floor plan depth, the 8-meter floor plan depth, is perfectly good for natural cross ventilation if the internal gains aren't too high. And so we went through an early process of identifying the right servicing for the different parts of the building, which was I think is quite, I wouldn't say it's unique, but it's a very important way of thinking about maybe how you do passive design as we move forward, looking ultimately with the goal being simplicity. Make it simple will always result in lower carbon emissions and lower embodied carbon, particularly for the services. And what you see on this image particularly is sort of getting the right amount of glass area, which is partly driven by the historic nature of the site and the context, but it's also driven around getting the right amount of light for area for daylight without getting too much heat gain or heat loss. And then what you see here, these hit and miss panels, as Matthew alluded to, are part of the ventilation strategy for the building. So level 1, level 2, we have some classrooms that are naturally ventilated completely, some classrooms that are mechanically ventilated, and some classrooms that actually have some active cooling due to high internal loads. So very, very detailed analysis of the needs of the project. And then we, over time, developed this sort of environmental diagram, which summarizes a lot of those decisions. And I'm going to go through it in a bit of detail in a second, but principally, just on the passive design, worth saying that we did a lot of work on the daylighting, trying to make sure the rooms are very well daylit. They're side lit daylight mostly, except for the butterfly roof that Matthew described. But and then the main, I guess, move in terms of the low carbon technologies was to use water source heat pumps to try and keep, so we have no noise from above ground equipment, which heat pumps can be guilty of, and a closed ground loop system, which is something we'd experimented with both at WWF and an open loop system at the Croon Hall in Yale. And so this is all about minimizing the carbon impacts in the operation of the systems by using very low carbon energy and all electric technology, so no gas, no emissions on site. And as I mentioned, natural ventilation was the first prize. We did analyze it using a program called MacroFlow, which is the airflow analysis that's embedded in the IES suite of computer software. So we were able to really be confident we could design for natural ventilation. Most of the aspects are dual aspects. Most of the space is a dual aspect, which is good for cross vent. And as Chris mentioned, the upper floor's got the louvers in the top of the butterfly, which allows stack effect and also sort of a certain amount of Bernoulli effect to increase the ventilation. And we use that analysis tool, MacroFlow, to size the ventilation openings to right size them. And we then used Building Bulletin 101 as our design criterion for overheating to determine both glazing performance and to understand particularly how ventilation would impact on temperature, and to understand a little bit about thermal mass in the building. Now, thermal mass is a really big sort of question with timber buildings. People, when we're aware that in a building that's thermally massive, you would often look for concrete, and in this building we wanted to make fully timber. So I studied what impact does this have on the overall temperature control. And just to give you, if anyone's interested in the numbers, I put these in. The cross-laminated timber has got a lower density and a slightly higher specific heat capacity than concrete. But that, because of a lower density, the heat capacity per kilogram is greater. But overall, in terms of the thermal mass, which is the function of density times specific heat capacity, CLT is only about 1/3 of the thermal mass capacity of concrete. But still, if properly deployed, it can help regulate internal temperatures. And of course, with schools, we do get the advantage that the schools are rarely, if ever, occupied during peak temperature times. You might get a little bit at the early part of the term in September, a little bit in June, July, but over time, it's not. We found in modelling that we're very rarely will we going to exceed the temperature limit with natural ventilation, and the benefit and the simplicity of natural ventilation and the reduced cost was very much worth taking. Matthew's already been through the embodied carbon comparison, but I think it's just important to sort of put as a coda to the end of that bit of the presentation that we were very involved also looking at the overall embodied carbon of the project as we went forward and trying to put it all together. And what you end up with is a certain amount of exposed thermal mass here, a certain amount of acoustic insulation, and then this nice section that's all detailed around cross ventilation. So I think quite a good integrated design for the project as a whole. Systems, we used 4-pipe ground source heat pumps, which means they can heat and cool. We've only got about 25 kilowatts of cooling capacity, but it runs quite a lot of the time because of the fact it's running cooling computer systems. We've got a buffer vessel that holds the water and allows us to sort of buffer against some heating and cooling. MVHR in the classroom, the labs and prep rooms, and then a natural vent in many of the classrooms, as we said, and a little bit of cooling where we needed it. The units, you can just see, I've got a sort of image here. This was the graphic that shows the MVHR and acoustic rated cupboard. Again, we were trying to absolutely minimize the amount of ducting. So these units just sit in the corner of the room and change the air several times an hour to give you the sort of managed airflow and managed air quality that we wanted. And then you see on the outside these hit and miss vents that allow the air to come in. And then the other elements were kind of the underfloor heating in the cloister area, perimeter radiator heaters in the other areas to deal with the facades, and a pretty simple design. And then finally, for renewable energy, the SciTech block has a PV array on the roof, which delivers some of the certain amounts of the power. The ground source heat pumps rated just 130 kilowatt peak. We've got two units rated at 75% each, and so they're doing heating and cooling. They can do both simultaneously if necessary. And of course, taking a low carbon fuel supply, that the electricity supply is bought from a low carbon supplier, it means your net heating and cooling has a very, very low operational carbon. The other thing with these sorts of timber structures, and particularly working with architects like Hopkins, is the MEP integration. This is a view of our BIM model, and every single component of the building was registered in the BIM model. And the tricky part of course, these buildings is that you really want to not see MEP on the surface of CLT where it is exposed. We were trying to we have a raised floor across the whole project with these cable trays, pipes under the floor, and so on as you expect, and then integrated into the wall structures, these rebates that allow us to hide a lot of the MEP services. My colleagues at Atelier 10 and their great lighting team did lots of work working with Hopkins for the multiple times now, looking at how do we develop a family of luminaires that provide the lighting, and then how do we integrate them into the ceiling structures. So this is an integrated light fitting into an acoustic panel, and you see it too in the cloisters that the timber acoustic paneling is all integrated seamlessly with the lighting. So again, these things don't happen by accident. They happen with a lot of hard work and a lot of modelling to really fully understand how this building was going to perform. So that I'll leave the diagram up. I think actually Matthew's going to take control again of the screen, but that's a very quick run through the kind of M&E and the environmental design approach for this great project.
Thank you very much. I'm glad you brought that slide back up there, Patrick, and gave it a bit more airtime because I thought it was really excellent. But yeah, thanks for all the presentations. Good to see lots of questions being asked and answered. I thought I might just start with, because there were just two very recent questions about the wall and the brick leaf. So I don't know, I noticed, Chris, you were actually typing an answer about that, but just because two people had asked about that, I'll quote one of them. To clarify the wall stratification, how the timber inner structure works with the external brick leaf. They'd also then gone on to ask about insulation and whether there was insulation between the internal and external layers. But yeah, there were two questions specifically about how the timber wall and the external brick kind of relate. I thought I would raise that one if anyone would like to take that.
Am I unmuted? Well, I think that there's a query about the brick leaf being 150 mil thick. I don't know where that has come from, but it is a standard brick. We did show some slightly larger bricks for the coins at the base, but actually I think we managed to avoid that in the end. And in terms of the movement, essentially we just tied it back to the structure, didn't we, Matt? It was stack
So we
bonded.
stacked all the way from the ground up. So you kind of the limit of what you can. We were at the limit of what it was, and I wasn't particularly happy with one of the bricks you picked either, was I, Chris? And it didn't quite work with the. Pushed you up on the strength, and actually we adopted lime mortar. So one of the neat ways that Chris' team came up with hiding movement joints in terms of vertical movement joints was using the gutters. So the gutters actually then you've got the language, haven't you, that matches the Baker building where they're external kind of cast iron things, and just made them like the modern version of that.
Yeah, exactly. That's why I was in the middle of typing. So essentially, where we needed a vertical movement joint, we managed to hide them behind the recessed downpipes. So that was the plan there.
Great, thank you very much. And Matthew, it looked like you wanted to say something about insurance in reply to one of the
So there are two things, like insurance and building control were two things that I thought might turn up. So the interesting, so here we were very clear to the client that they should go and talk to their insurers before. So like at stage 3, we said this. The interesting thing here is they've got very specialist insurers because of the rest of their site. They've got grade 1 listed, they've got grade 2 listed. They've got lots of things. I mean, all those buildings are effectively they're masonry timber buildings, but with joists, aren't they? So they're really very high risk in terms of fire. And they were spectacularly relaxed about this, and they didn't want to ask any questions. It's the only project I've had where they've been so like, yeah, we're fine. It's everything else on the site is so risky that we'll go up a little bit because you've got more building, but it didn't massively jump up the rate. So I think it was just, I flagged it because it was an interesting one because of the risk of the entire site. It wasn't an issue at all on this particular project, but it is quite often on other projects.
I think it was early engagement as well.
Yes.
We definitely
early engagement with everyone.
With the school, particularly, and just to flag that
they should have that conversation.
Potential, with the insurers.
Rather than waiting to the end just as they're about to open it and saying, "Are your insurers happy with this?" We made sure they had that conversation early and had because yes, we have experience of that being more challenging than it was on this particular project.
Thank you. This isn't really a question so much as sort of observation. I thought it was really interesting in both a couple of points you made, Matthew and Patrick, about the kind of, I suppose, seesaw of considerations when you're really trying to cut embodied carbon to LETI or iStruct targets. I sort of made a note, Matthew, when you were talking about the thickness of the CLT floor and how obviously from one point of view, yes, you want to be as economical with resources as possible, but on the other, the sort of seesaw of that is that you had extra benefits in terms of vibration, acoustics, and I think even fire. I think you mentioned sort of charring. I just wondered if you wanted if anybody wanted to say anything more about those sort of decisions and those sort of considerations in kind of weighing up how one thing affects another and sort of trade-off in design and specification decisions from that point of view.
I guess it's having those open conversations with the rest of the design team, because also if we went for downstand beams, that very much changes the way that the lighting works. And so I think that was one of the tenderers even offered that as a potential cost saving, and I think the team kind of looked at it and went, well, the number of things that changes in terms of how the building is serviced was why we ended up where we ended up. So it's basically not working in a silo. So I could provide the the bare minimum in terms of structure. Chris could provide the lowest carbon like finishes as possible, and Patrick could provide the best system in the world. But because each one of those then impacts on everyone else, we've got to make sure that we are talking all the way through about why we're picking what we're picking and whether there's any impact on the rest of the team. Yeah, I don't know if that chimes with Chris and Patrick.
Yeah.
Yeah. Well, I mean, I suppose I was also thinking of, Patrick, what you were saying about, daylighting, of course, and the amount of sort of glazing used and those considerations.
Yeah, I mean, I think it's important. That's increasingly important, as because building regs has been driving down glass areas in response to thermal concerns. But in reality, or in our new world, as our power companies have sort of reduced the carbon intensity of power delivered by 60% probably since 2013, 2014, when they were just about conceiving the building regs that we currently work to. So the impact of heat pump generated heating, which is the consequence of a bigger window, is actually vanishingly small at the moment. So I'm a bit of a radicalist. I think that actually making windows tiny runs counter to both energy efficiency and the quality of life and light in the buildings. So I think there is a very strong emerging argument that actually we need to be thinking more about the quality of space and the quality of light that we put in, and the positioning of light, and this is an even bigger issue, I think, in residential probably than in this sort of building, where the windows are getting vanishingly small and disappointment and result in poor spatial quality. So this convergence of the operational and embodied carbon is a really important thing at the minute. We just see it and it's difficult to analyze, because it is that you do have a consistent metric, which is kilograms of carbon per square meter. And so you really can now compare, because we're now able to do all these calculations to look at the carbon impact of structures. You can look at the 30-year impact quite easily when you look at the operational carbon, the embodied carbon on this against the same metric. And often the embodied carbon now is much bigger, which is the carbon we put into building the thing in the first couple of years, much bigger than the 30-year operational carbon, particularly on a simple building like this. So the game has changed fast, and I think Matthew's point about us all talking a lot and being understanding these issues together is absolutely fundamental. And I think having teams that have worked together as we have with Hopkins and Integral for years, you kind of get that kind of understanding of how you have that conversation. It's a super important one right now.
Thanks. One thing I just wanted to ask, because I'm not sure it was covered, was just how long it took, how long construction actually took. Was it a speedy build?
Yeah, so the timber frame itself was 12 weeks. It split, as I mentioned. So they did the two main blocks and then came back, but it was 12 weeks was BK on site. And then I hand it over and I come back at the end. So Chris can tell me for the rest of it.
It was just over a year, start to finish on site. I think in the end, definitely the CLT frame helped with that 100%. Definitely sped it up. It was slightly delayed, opened in November, should have been, well, ideally start of September. School could have opened it, but yeah, that was the plan anyway.
Great, thank you. Well, I think we've more or less covered everything. Unless anybody would like to add any other sort of final kind of take homes from any of the panel. I suppose any other aspects to the design or the construction that you're particularly proud of, that you'd like to sort of leave us with. We had one. Well, I mean, obviously you've given great presentations, so we covered that. We had one question that's just come in, asking if there was anything, if you had to do it again, that you might possibly kind of improve on.
I don't think it's related to technology or advancements in technology as such, but the stairs with the stone in general wasn't great, and the stone treads on the CLT stair. There are a few issues with that. I won't go into too many details, but don't look at the pictures too close.
Okay.
Yeah.
There are
it was
plenty
quite
of
a difficult
very,
detail to sort out in the end.
yeah, there are plenty of other beautiful pictures to look at elsewhere.
And I
Yes,
think
well,
oh, sorry, I was going to chip
go
in.
ahead.
One of the things that I would love to see in the future, that potentially using those timber acoustic panels to mix in some kind of phase change powder into whatever makes those. So you get there's companies make a powder called micronal, which basically it massively increases the thermal storage capacity of a piece of elements of material by changing phase from solid to liquid. So it doesn't really go liquid, but it's a game changer in terms of thermal mass, and it makes timber structures much more, it brings them up to the level of concrete, if not better. So if you could find a way to mix that and make an acoustic panel that does phase change thermal storage and integrates the lighting, then I think it's a win-win, and helps the timber to be more relevant across lots of different building types. But it's a slow moving technology, but it's one that I think is going to be very interesting in the future.
That reminds me, when you were talking about thermal mass, it made me want to fly the flag for wood fiber insulation, and excellent timber related products that has achieves very high thermal mass, and I believe it helps to keep buildings cool in summer and warm in winter. We have many TD UK members who can help anybody who's interested in wood fiber insulation out with their questions. You can find out more about that on our website. But yes, we've had lots and lots of compliments in the chat for an excellent webinar. Great presentations from all three of you. So I think we're just running a bit over 2 o'clock. So I will draw things to a close. Thank the panel again, and wish everybody a great afternoon. Thank you very much.
Thank you.
Thank you.
Thanks. Bye.